I've written a console program to do the performance measurements, and I'm using a base class called performance test right here to run the performance, the different performance tests. I have three methods here: measure test A, measure test B, and measure test C. So these are virtual methods, and in any derived class I will put the test code in here. And the format is always that the first one, test A, is the baseline test. So this would be unmodified slow code, and then we have two methods B and C available to try out different kinds of optimizations. And then for the actual performance test down here, the performance test is fairly simple. Basically what I do is I go through these test A, test B, and test C methods, and I repeat them a number of times. So you can see there's a constant here, default repetitions, with a value of 10. I basically repeat the tests 10 times to average out the effects of the garbage collector, because an ill-timed collection of the garbage collector can really slow down one of the tests. So if we just run it 10 times, then we average out that effect. To measure performance, you're supposed to use the stopwatch class in C#. So when you're doing benchmarking, please don't use date time. Always use stopwatch, because stopwatch is a specialized class for measuring time spans extremely accurately. So you can see I always start by restarting a stopwatch, doing the test, stopping the stopwatch, and then I have the elapsed milliseconds right here, and I'm adding that to a variable. And then in the end, you can see right here, I'm returning that total value divided by the number of repetitions. So we're doing 10 repetitions, so we have the total elapsed time for every method, and then divided by the number of repetitions gives you the average execution time. Okay, so the next thing we're going to look at is string handling. So this is a classic example of C# performance optimization, and yet I'm surprised by the number of people who don't realize this crucial difference. This is the code that does the test. The first, the baseline test, simply builds a string. So we start with an empty string right here, and then in a simple loop, I add one character to the string. And I do that 50,000 times. So in the end, I have a string of 50,000 characters, so that's 100 kilobytes on the heap. And that's it. The B test does the exact same thing, but it uses a string builder. So instead of adding strings together, it uses a string builder, and it uses the append method to append the character. The third test builds up a string incrementally, and it uses pointers. So you can see here that I start with a character array of 50,000 characters. Then I fix that character array on the heap, and I ask for a pointer to that block of memory. And then I declare my own pointer and initialize it with this initial value. So the pointer will initially point to the first element in the character array. And then in a simple loop, I use the pointer to directly write this character into heap memory. So this is a very interesting test, because it will show us how much faster string builder is compared to a regular string, and if it's worth your while to use pointers instead of using the string builder to speed up your code even more. So let's do the test and see what happens. So I'm running test 1, the string test, 50,000 iterations with a baseline. And here we go. Dum, dum, dum. And there you have it. So 553 milliseconds for the string, and the other two tests, they actually did run, but they are so fast that we can't see them on this resolution. So, I mean, you're getting a hint already, that the difference in performance is massive here. So let me run the test again. So now I'm going to go to 1 million iterations, and now I have to disable the baseline test, because then otherwise we have to wait forever. And check this out. The string builder takes 2 milliseconds, and the pointer operation is now so fast that we can't see it. So I'll do this again. And now I'm going to do 100 million iterations, again without the baseline test. Let's wait for it. And here are the results: 452 milliseconds for this string builder and 169 milliseconds for the pointer. So there is this massive performance difference between using strings and using the string builder. And if you want ultimate performance, you can use direct pointer operations on the heap, and that'll get you a roughly threefold performance boost over using string builders. So if you're wondering why is the string so incredibly slow, it's because of this. Let me show it to you in a picture. When you append characters to a string, strings are immutable in .NET. So that means that any operation that modifies the string will create an entirely new string on the heap. So in the first loop iteration, we have an empty string, and then I add one character, so I get a string of a single character on the heap. Then I add another character, and now I have two strings on the heap, the original and the modified version. Then I had a third character, and now I have three strings on the heap, the original, the modified version, and again the modified version, and so on and so on. So if I add 50,000 characters to a string, I end up with 50,000 disposed strings on the heap, where each string is one character longer than the string before it. So it's a huge amount of data that I'm flooding the heap with data, and I'm constantly doing this memory copy operation where the string is being copied to a new version and to a new version and to a new version. So once we hit the higher end of the loop, like the high loop iterations, we're copying this block of 100 kilobytes on the heap. It's like 100K and then 100K plus 1 byte and then 100K plus 2 bytes and so on and so on. So it's super inefficient. If you use a string builder, it works the way you would expect. You have this buffer in memory that can hold any number of characters. You can declare a string builder and specify the size, and then you simply write characters into specific locations in that buffer of memory. So naturally, the string builder is much, much faster. Now, the fun part is that the string builder behind the scenes, the string builder is actually using this code. So internally, the string builder fixes a block of memory and then writes directly to that memory using character pointers. And the only reason why we see a difference between these two blocks of code is because in test B, we have the overhead of the append method, and that will slow down the code a bit. So going back to the results, the string builder, when you're modifying strings, always use a string builder because it's way faster. I mean, 50,000 iterations for the string and 100 million iterations for the string builder. I mean, that's pretty obvious. But if you want ultimate performance, use pointers directly. That'll give you another threefold improvement over the string builder.